Hello everyone, my name is Cristiane Garcia and I'm going to present a work entitled The Constrained Total Least Square Solution for Virtual Reference Feedback Tuning. I am with Federal University of Rio Grande do Sul and Professor Bazanella is my advisor. That's how I divided the presentation. First, I present an introduction where I present our motivation and our proposal. Then I present the original solution of the VRFT method and the solution that we are proposing to apply. After that, I present the results and finalize with some conclusions and future work. So, the task of adjusting the parameters of a feedback controller may be accomplished through model-driven methods, data-driven methods, or a mixture of those. Model-driven methods require the knowledge of the process model, and this is used to calculate the controller. On the other hand, when using data-driven methods, there is no need to know the process model, and the controller is calculated directly from the data. The non-iterative data-driven methods are those that require data from a single experiment to estimate the controller's parameters. I cite here three well-known examples that are the virtual reference feedback tuning, the correlation-based tuning, and the optimal controller identification. Perhaps the most exploited data-driven method in the literature is the VRFT. This method has already been extended to several cases, such as process with non-minimum phase zeros, multivariable process, and the recursive solution. Of course, in the literature, there are many other works that apply the VRFT to real process. However, all these works apply the same original solution proposed by Camp and others. The VRFT's original solution is commonly known as ordinary least squares, and it's known that solution leads to a biased estimate in the presence of noise. As an alternative, the literature suggests the use of an instrumental variable, which gives an estimate with less bias, but with more variance. With that in mind, we propose to apply a different solution, already existent in the least squares literature, to the VRFT problem to reduce the bias of the estimate. So, our objectives here are to apply the CTLS solution to the VRFT's problem and to compare the results obtained with the CTLS, OLS, and IV solutions. Summarizing, the main contributions of the present work are to show that the VRFT problem may be formulated as a CTLS problem and to derive the solutions for the open and closed loop cases. It's worth to mention that we expect great performance improvement. The application of the VRFT method is presented here as a sequence of steps. In the first step, the data is collected from an open or closed loop experiment. In the second step, we generate the ideal controller's virtual input signal, and the signal is generated by filtering the output signal by a filter that depends on the reference model. The last step is to identify the ideal controller's parameters, usually solving a least squares problem. In this figure, it's presented the case of a linearly parameterized controller. The controller's parameters are estimated by solving this equation. In vector form and considering the noise-free case, we have this model, where the subscript 0 indicates that the quantities are not affected by noise. However, this is not a realistic case, since in practice the signals are always affected by noise. This way, we rewrite the model as this equation, where delta phi represents the noise contributions in the regressor matrix. In the VRFT problem, this matrix is always affected by noise because it's calculated from the output signal. And delta U represents the noise contributions in U, which is only presented in closed-loop data. The least square solutions are classified depending how the noise affects the signals. The original solution, for example, considers that the noise affects only the output. The optimization problem is this, and the solution is well known and is given by this equation. Therefore, the solution does not fit well to the VRFT problem since it does not consider the noise in the regressor matrix. As a consequence, we have a biased estimate. In order to reduce the bias of the estimate, an IV is used. Among the options, we choose the one that requires repeating the experiment with the same input signal to collect more data. So, we generate two pairs of signals, and the solution is given by this equation, where each regressor matrix is generated by one dataset. The drawback of the solution is a high variance in the estimate that may lead to performance loss and sometimes instability. Let's talk now about the CTLS solution. The solution is well known in the least squares literature and it was developed from the total least squares problem, with the constraint that the same noise source affects phi and u. The optimization problem is formulated as presented here and considers that we know the Toeplitz matrices, Pi. That means that we know how the noise V affects each column of the matrix formed by delta phi and delta u. The CTLS solution is given by solving this nonlinear optimization problem, and we need to define the filters that will generate the matrices Pi for the open and closed loop cases. These filters come from the VRFT signal, and for the closed loop case we have m+1 filters, while in the open loop case we have only m filters. Now I will present the results. Here I present a setup for each case study, where we have run 100 Monte Carlo simulations. This is the process transfer function used in the simulations, and that is the reference model chosen. The ideal controller is a PID given by the ideal parameters vector multiplied by the controller structure. The process output is affected by a white noise filtered by this model, and the variance of the noise is different depending on the case study. In order to compare the results, we are using two metrics: the estimated cost function, which is calculated for each realization and using the parameters estimated with each method, and the estimated mean squared error. The parameters are estimated using the original solution, the IV solution, where a single experiment with a periodic signal is performed and the data is split in two, and using the CTLS solution with this configuration. It's worth to mention that the noise model is not used in the filters, since in practice we do not have this information, and that the sensitivity function is approximated by the ideal sensitivity function. That depends only on the reference model. It's also worth to mention that other optimization algorithms and/or initial guess could be used. In the first case study, we are using data collected from an open loop experiment. As input signal, we are applying a square wave with two periods, and the signal-to-noise ratio is approximately 34 dB. One realization of the input and output data is presented in the first figure. In the second figure, we present the histograms of the cost functions obtained with each method. Note that the CTLS solution yielded a performance roughly 9 times better than the OLS. The IV approach gives results widely distributed. That's because the IV approach is known to yield an estimate with pronounced variance. The parameters MSE are here, and the smallest value is obtained with the CTLS, while the largest value is obtained with the OLS approach. In the second case study, we are using data from a closed-loop experiment. The reference is excited with the same square wave presented before, and one realization of the input and output signals collected is presented in the first figure. The signal-to-noise ratio for this case is approximately 26 dB. The histograms of the estimated cost function calculated for each method and are presented in the second figure. The CTLS approach gives results roughly 10 times better than the OLS. Again, the IV solution presents widely distributed values. These results also agree with the values obtained for the parameters MSE. The last case study uses data from a closed-loop experiment. In fact, it uses the same setup presented before. The difference is that we increased the noise level. The signal-to-noise ratio is approximately 18 dB, and one realization of the data collected is presented in the first figure. The second figure presents the histograms of the cost function. The OLS approach gives values 10 times higher than the OLS again. Also, the smallest value for the parameters MSE is obtained with the CTLS approach. The results obtained with the IV approach are not presented here because approximately 20% of the controllers resulted in unstable closed-loop behavior. Now I will present some final thoughts. The original VRFT solution leads to a biased estimate in the presence of noise. To reduce the bias, an instrumental variable is used with the drawback of increasing its variance. In order to deal with the noise, we proposed to apply the CTLS solution to the VRFT problem. The results have shown a 10 times improvement compared to the OLS approach. As future works, we intend to compare the results obtained against other data-driven methods as the OCI and to apply the CTLS solution to the VRFT multivariable case. We also intend to apply the CTLS solution to other data-driven methods such as the virtual disturbance feedback tuning. Thank you for your attention.